Thanks. Let's begin with a word of prayer. So, Heavenly Father, we, again, Lord, thank you for this opportunity we just have to meet together, study your creation. We thank you we can talk about you openly. We thank you for all your many gifts to us, that you love us even when we didn't love you, and we just thank you for your grace, which is more than abundant for us, Lord. Let's pray you guide us today. Help us to glorify you again, Lord, what we do. In my prayer, Lord Jesus. Amen. So I had a request for section 7.7, number 32. I reserve the right to not do this because it's lengthy and irrelevant, but that may not be the case. Oh, differentiate. Yeah, this one gave you guys a lot of trouble last cycle. I don't know why. Let's see here. Y equals 2 x over the square root of c squared minus x squared, right? Minus the inverse sine of x over c. And we let c be greater than 0. All right. And the question, I guess, is just to differentiate it. This is the problem? All right. So, unlike the problem in the quiz, this is, I really don't know anything to do here except to just differentiate it directly. And just gotta be careful. dy dx. So, quotient rule, right? So, I have the derivative of the top function, which is 1, times the bottom function, square root of c squared minus x squared, minus x times the derivative of the bottom function, which is minus 2x over 2 times the square root of c squared minus x squared. That's all divided by this gadget squared, which is c squared minus x squared. All I've done, of course, is to differentiate the first term, right? Second term, I do minus 1 over the square root of 1 minus x over c quantity squared times the derivative with respect to x of x over c. Now, why did I do that? This is chain rule, right? The chain rule, because the derivative with respect to x of like inverse sine of u is 1 over the square root of 1 minus u squared times du dx. You know, that's what I'm doing here. How do I know the derivative of inverse sine is 1 over the square root of 1 minus u squared? Well, we worked that out yesterday, right? Or you should know it from your previous course and your more gifted and attractive instructor. Let's see here. Or at least more attractive. Let's see here. So, I don't know. Then what?
Isn't it 1 over c? Because you take the derivative of that? Because...
1 over what?
Right here, or x over c. Wouldn't it be 1 over c? Because you take the derivative of x over c?
Oh yeah, this is, this simplifies to 1 over c, right? Now c is positive, so we can rewrite this a bit. We've got ourselves square root of c squared minus x squared minus, let's see, what's that give me? That gives me plus x squared over the square root of c squared minus x squared, all divided by c squared minus x squared. And this over here, if you multiply the c inside, what does that give you? It gives you that. See, the reason for that is 1 over c times 1 over the square root of 1 minus x squared over c squared is equal to 1 over the square root of c squared times 1 minus x squared over c squared. And so that's why I got that. I mean, technically the differentiation is done in the step above, but if I was to ask you to simplify, we're still not done, right? We can simplify this further, right? How would you simplify it? I think what I would do would be, I want to clear, I don't like this. So I want to create a common denominator of like c squared minus x squared to the 3/2 power. Right? So what's that do? If you look at that, it gives us c squared minus x squared plus x squared divided by c squared minus x squared to the 3/2 power. If I multiply this by the square root, top and bottom, cancels out in the second term, becomes a c squared minus x squared in the first term, downstairs 3/2 c squared minus x squared, right? And then over here, yeah, go ahead.
I think you need to square the denominator.
I did.
in the initial.
I did. So c squared minus x squared, like that. So over here, basically I have to multiply this by c squared minus x squared over c squared minus x squared as to create a 3/2 power there, right? So you put that all together, stuff cancels, right? And you're just left with the x squared over c squared minus x squared to the 3/2. And I say that's simple. I mean, that's as simple as I'm going to get it. I don't think there's anything here you don't know. You just have to keep at it and be careful, right? Other questions? Yeah.
Can you explain the part in green again?
So we had up here, right, this is just 1 over c.
Right.
So I just put it in front for no particular reason, mostly to confuse the students, to emphasize it's going inside the square root. When I bring the c inside the square root, it becomes a c squared, but then I have to distribute it across the 1 and the x squared over c squared. C squareds cancel here, leaving me x squared, and c squared times 1 is just c squared. See, so this term right here is the same as this term. Yeah. The larger game plan here is I've got these square roots of stuff floating around, right? I want to make them all look the same. So I chose c squared minus x squared as my target. If I wanted to be weird, I could have tried to make them all look like the square root of like 1 minus c squared over x squared, but glad I didn't. Other questions? Let's take a look at number 33 in 7.7. In my experience, this is a good problem for you guys to look at for a minute. Here we're given a triangle, right? It's a right triangle. We're told that the length of this side is x. We're told that the length of this side is 1. And we're also told that in here we've got inverse sine of x. All right? And what you're supposed to do is to use this triangle to figure out various trigonometric things, like what's the, for example, cosine of the inverse sine of x equal to? Or what's the tangent of the inverse sine? And so forth. I personally think this problem's more exciting if you erase inverse sine and put a theta, but you know? Because then it's easy, right? Like cosine of theta is what?
Adjacent over hypotenuse.
Yeah. Okay, so what is the adjacent side though? Square root of 1 minus x squared. Very good. Now how did you know that? Pythagorean theorem, right. So, yeah, this is what? This is square root of 1 minus x squared divided by 1. Now, if you were in the tutoring center with my friend Somber Paul and you divided by 1 on your calculator, that was a near-death experience for you. Like, it made him angry. Very angry. But for us, it's, okay, so fine. This cosine of inverse sine of x is equal to the square root of 1 minus x squared. There you go. For example. So what's the tangent of inverse sine now that we've done one of these? Right, x over square root of 1 minus x squared. Now these kinds of substitutions become important as we get into the trig substitution section in a bit, all right? So just shout out for number 33 here. Let me take a swing at something a little bit more difficult. How about Dr. Skimbortis was tempting me with something. I probably shouldn't, though. Yes, I'll behave and ignore Dr. Skimbortis. So here, I should talk to you at least a little bit about theorem 7.9.2, though, and we'll pick one of these to try to prove, because these are really neat formulas, and they're on occasion they come up, but they do give us some good experience with calculating these sorts of things. Inverse hyperbolic sine of x is allegedly the natural log of x plus the square root of x squared plus 1. And that's for x real. For real, all right, there, sorry. And there's also a formula for cosh. Cosh inverse of x is equal to the natural log of x plus the square root of x squared minus 1. So if you look at the formula there, x squared minus 1, that's only going to work for what? For x not too small, right? X has to be bigger than 1 in magnitude. So this is going to be for the absolute value of x greater than 1, maybe equal to? Well, greater than or equal to. Otherwise, that root wouldn't make sense. That's kind of a dead giveaway. And then there's also a formula. This is 1, 2, and 3 in that theorem. The third thing is that the inverse hyperbolic tangent of x is 1/2 the natural log of 1 plus x over 1 minus x. All right. I forget when it happens, but at some point we find ourselves in some sort of dark corner, and this theorem helps us understand where we are. So it's, I mean, these are not things I know off the top of my head, all right? Like, I have to look these up when I need them personally. So let's work on number 1. Actually, it's a really great exercise in algebra. So what we want to try to prove 1, all right? I guess 1 is in the book. Maybe I should try 2, since you can look at 1 in the book, huh? Oh no, they have 1 and 2. What do they have 3 in the book too? Oh, 3 is left as an exercise. That seems scary. All right, I'm gonna do 1. So we have, we're trying to understand this identity. We're trying to connect the hyperbolic sine to the logarithm. I think a good starting point for this would be to do something like, let's say y is equal to inverse hyperbolic sine of x, right? We're basically trying to show that y is equal to the natural log of that stuff, right? So the next thing I would do is I would take the sinh of both sides, right? The hyperbolic sine of y is equal to x. But what is hyperbolic sine? Do you guys remember? We talked about it yesterday. We defined it. Somebody tell me? 1/2 what? I take your x and replace it with a y, but yes. E to the y minus e to the minus y, because we got sinh of y here, right? But your heart was in the right place. I can't fault it. Right? We're trying to solve for y, right? That's our goal, solve for y. How do you do that? But natural log doesn't like differences. Ooh. Sorry. Bad memories already. Let's see here. How about this? This is e to the y minus e to the minus y equals to 2x there. That's a little bit better, right? Sort of? Kind of? Let me do something. If I multiply this by e to the y, what do we get? I get e to the y squared, right? Minus e to the y times e to the minus y, which is 1, right? Equals to 2x e to the y. Wait a second. If I rearrange this just a little bit, what do I got? I've got e to the y, quantity squared, minus 2x e to the y, right? Minus 1 equals to 0. Let me rewrite this a little bit. What we're looking at is Pac-Man squared minus 2x Pac-Man minus 1 equals to 0. Where Pac-Man is what? Right. It's quadratic in Pac-Man. Hey, quadratics, we own those. We can solve it, right? You can complete the square to solve it if you want. You guys look a little tired. I'm just going to write the formula here. So basically, Pac-Man is equal to what? So this has what? A is equal to 1, right? B is minus 2x, and C is equal to minus 1. I know you're used to working with x playing the role Pac-Man does here, right? So maybe I'm blowing your mind a little bit, but the coefficient has an x in it this time. So minus b, right? Plus or minus the square root of b squared minus 4ac divided by 2a. So that's like 1/2. Minus 2x is 2x. Plus or minus the square root, let's see here, b squared, which is 4x squared, minus 4ac, which is minus 4 times 1 times minus 1. Let's see here. That is, in fact, 1/2 2x plus or minus. Oh, there's a 4 that pulls out here, isn't there? So look at that. That will pull out to become a 2, right? So this is exactly x plus or minus the square root of x squared plus 1. And that's equal to what? Pac-Man. What was Pac-Man? E to the y. So then what do we do? Yeah, solve for y, right? How do you solve for y here? By the way, let's see here. Oh, huh. One of these solutions is extraneous, right? Like the minus x squared plus 1 is what? It's always larger in magnitude. The square root of x squared plus 1 is larger in magnitude than x. So like this minus, I think is always going to give us a negative value. The exponential can't be negative, right? So we have to choose the plus in order to get a solution. What's that?
I said, which means you can do the natural log.
Yeah, yes, I mean, right. Also that. So the natural log of x plus the square root of x squared plus 1 then is equal to y. But that's exactly what we were trying to show. And the argument for the other formulas are pretty similar. Now, I showed you how to differentiate inverse hyperbolic tangent yesterday, right? We found out it was 1 over the square root of 1 minus x squared. Is it all clear to you that the derivative of the inverse of this formula is 1 over the square root, 1 over 1 minus x squared? Like we proved yesterday, right? Uh-oh. Yesterday we worked out that ddx of inverse hyperbolic tangent of x is 1 over 1 minus x squared. Is that right? I'm always debating whether or not I forgot a minus in here, but this theorem claims that inverse hyperbolic tangent is equal to what? 1/2 the natural log of what? 1 plus x over 1 minus x, right? Is it at all clear to you if we differentiate this, we get that? It's clear? Should we work it out? Let's try it. Let's try it out. Let's see how it goes. Let's check what happens here. How would you differentiate 1 plus x over 1 minus x? So what I'm doing is I'm checking consistency at the moment. I'm really just trying to show you another example of differentiation. I think it's helpful. So how should you differentiate something like this? You should not just differentiate this, right? We should use log properties. So I pull out the half, and I have the derivative with respect to x of the log of 1 plus x minus the log of 1 minus x. Right? That is much easier to differentiate. So then I differentiate that. I get 1/2, 1 over 1 plus x, minus a minus 1 over 1 minus x by the chain rule. Now we just have to make a common denominator, right? 1 minus x plus 1 plus x divided by 1 plus x times 1 minus x. You notice the x's cancel. You get a 2 in the numerator. That cancels the 2 in the denominator, and voila. So in principle, you could take a different path to the development of these inverse hyperbolic functions. You could just tackle Mount Algebra, prove these formulas, right? And then extract derivatives of the inverse hyperbolic functions from just hand-to-hand combat with logarithms if you wanted to, if you don't like the argument I showed you yesterday. I think the argument I showed you yesterday is way easier though, right? I mean, we haven't done it, but I'm guessing the derivation of 3 is at least as unpleasant as what we just did here, right? Which isn't impossible, but you know. All right, any other questions about homework? Otherwise, I'm going to move along here. Let's move along then. So this brings us to chapter 8. And the first, so basically we go straight to section 8.2. In order to be successful at integration, you need to know all of your basic integrals, right? What are the basic integrals we already know? We know integrals of sine, cosine, cosh, sinh, power functions, square root functions, cube root functions, right? Exponentials. But there are other things we don't know how to find the integral of, right? For example, the logarithm. We don't know how to integrate log yet. We have an integral which works out to log, right? But the integral of log, we don't know. There's some things we know how to do the integral of from u substitution. There's a fair amount there, right? But past that, what do you do? The next technique that's important to know about that solves a large variety of problems that come up in applications and elsewhere is so-called IBP, otherwise known as integration by parts. So here is basically the point. If we take the derivative with respect to x of u times v, right? Well, there's a product rule there, right? U and v are functions of x. This gives us what? This gives us du dx times v plus u times dv dx. Excuse me. All right. So, what happens when you integrate the product rule? We're doing an indefinite integral, right? I'm using linearity here. What's the integral of a derivative? It's what?
Wouldn't it just be v for that?
The integral of a derivative is the antiderivative.
More specifically, the thing I underlined in bluish, whatever this is here, what is this? Oh man, they give it no kind of flowery name or anything. You know, you pay good money for these. They don't even come up with some kind of stupid name for them. It's kind of disappointing. You buy a package of crayons for nearly no money, and they got all these kinds of crazy names for the crayons, you know? This is just UV, right? I'll put you guys on measure. I mean, somebody probably said, you may have said that already. I just didn't hear it. Sometimes it's the voices in my head. Okay, so the dx's cancel here, right? In terms of like a u substitution. And then you have what? You've got like integral of v du plus the integral of u dv, right? Making a u substitution and a v substitution. Well, this is integration by parts. Now, traditionally, what we do is we say the integral of u dv is equal to uv minus the integral of v du. And so, at least in American standard calculus, it is a matter of tradition to use these letters in these ways. And there it is. This is the integration by parts formula. If I go through the same derivation for a definite integral, what happens? If instead of looking at indefinite integration, what if I integrate, say, this from a to b?
It's the same one.
Right. Basically the same song and dance, except when I get down to here, I should do from like v of a to v of b, and this would be from u of a to u of b, and this would be from a to b. Now if you don't like that, you could also write it this way. The integral from a to b of u dv dx is equal to uv integrated from, evaluated from a to b, minus the integral from a to b of v du dx. So you pick your poison. If you do u substitution and v substitution, you have to change the bounds to corresponding u of a, u of b, v of a, v of b. Anyway, sufficient to say that integration by parts also works with bounds. You just have to let the bounds follow along in the natural way. Okay, so let me show you an example of how this actually works. The integral of x e to the x dx. All right, so what I'm going to do is I'm going to call this bit right here dv, and I'm going to call this guy u. So to make integration by parts work, I have to identify both the u and the dv. There's two moving parts. You have to make both of them, adjust both of them so that they fit the integrand that you're given, if it's going to work. Okay, having identified them, and I'll write over here, u equals to x, and dv is equal to e to the x dx. Now think about this. In order for this method to work, first of all, you have to be able to differentiate the u. give me an example of a u that you can't differentiate. Can you give me one u you can't differentiate? What was your name?
Seth.
Seth? It's a mean question. It's about impossible to come up with a function you can't differentiate. That's kind of the embarrassing thing about Calculus 1. We can differentiate everything, right? So this step is safe. Whatever you make u, you can differentiate it, pretty much, right? Setting aside functions that only mathematicians can create. But this, dv, right? In order to find v, how do you find v from dv? You integrate. So your choice of u is not isolated, right? Whatever you choose for u forces dv to be a particular thing. And dv has to be something that you can integrate in order to make this work directly. Can you integrate this? What is v here if dv is e to the x dx? V is equal to e to the x, right? You don't have to add a constant for reasons that become clear as we go on. Excuse me. All right, so then I go back and I use the integration by parts formula. Let me erase this clutter. And I'm going to write it down sort of symbolically before I put the things in. uv minus integral of v to u. All right. So u and v is x e to the x, right? Minus v was what? What did I just say? Oh, e to the x. What's du? dx. Yay. So we know how to integrate that. Integral of e to the x is e to the x. So I have x e to the x minus e to the x plus a constant. And there you have it. That is the integral of x times e to the x. That is something we could not have integrated with u substitution. Unless you're more clever than I am. That wouldn't be hard, but I don't know how to do it. I mean, I guess you can always, well, let me shut up. Any questions? Best thing to do at this point is to look at more examples. So next example here, I'll call this example 1, example 2. Let's look at the integral of inverse sine of x dx. Now, I definitely can't make v equal. I can't put the inverse sine in the dv, right? Because I don't know how to integrate inverse sine yet, right? So it pretty much forces me to make u equal to inverse sine if this is going to work, right? So I'll make this be my u, and I'll make dx be dv. So I write over here, just to keep things organized, u equals to inverse sine, dv equals to dx. I seem to have violated my my template. Oh well, you can forgive me. Dx over the square root or not. I mean, if you don't want to, you can hold a grudge. I can't stop you. Let's see here. But surely you could find better people to hold grudges against, especially in this presidential election. Let's see here. There's so many people that you could be angry at. Let's see here. Who am I kidding? You guys probably felt the burn and now you're sitting it out. Am I right? No? My little sister? Like, that's good, Mary. Sit it out. Thank you. All right. So that worked. Well, I don't know if it worked yet, right? So now we do uv minus the integral of v du. I'm getting tired of writing this. I'm writing it for your assistance. You don't have to keep writing uv minus the integral of v du as we go on here. It's kind of like, you know, when you first start riding a bike, you got training wheels on. You know, you don't have to leave them on forever. That's what this step is. Okay. Okay, so uv is what? It's x sine inverse of x. I wrote the x first for matters of good taste. And then minus the integral of v to u. So that would be x dx over the square root of 1 minus x squared. You're like, oh man, well that's no good, right? Is it? Is it no good? What do you already know from Calculus 1? What have you already forgotten from Calculus 1? Sorry, yeah. Make a what? Yeah, I thought you were saying something.
Oh, no, didn't say anything yet, but you used U substitution for x.
U substitution. Oh, you're like U substitution. Yeah, maybe. I think if you're going to make a second substitution and you've already used U, obviously the next substitution should be W, right? So W substitution. W equals to what?
dx. Or dx.
This is the offending thing here, right?
Sorry.
1 minus x squared.
1 minus x squared. You know, if we met 2 hours a day and also on Saturdays, I would try out all the things that don't work in front of you. But I figure we meet enough already, right? So I'll do the things that work mostly. On occasion, of course, I'll do something that doesn't work on purpose, just because that's just what I planned. But we haven't gotten there yet. So dw is minus 2x dx, right? So this is x inverse sine of x. That minus and this minus come together. We get plus 1/2 the integral of dw over the square root of w. Of course, that's w to the minus 1/2 power, right? Or, I mean, more to the point, your integrand is basically 1 over twice the square root of w. So that's the derivative of the square root w function. So the antiderivative of that is just square root w. So we get x sine inverse x plus the square root of w plus a constant. And then finally, we shouldn't leave it in w's. We should try to write it nice and neat. We got x inverse sine of x plus the square root 1 minus x squared plus a constant. And there you have it. So integration by parts sometimes also requires U substitution. It's part of it. Does this make sense? I mean, there's a lot of questions to ask here, right? If you've never seen integration by parts before. A lot of you have seen this before, right? So, for those of you who haven't seen this before, do not be terrified by the fact that you seem to be surrounded by people who know what's going on. They've been down this path before, you know? You can ask questions when you have them. Let's see here. What else? Oh, logarithm, right? We don't know how to integrate log yet. Let's try that one out for size. What if we were trying to integrate? I'm going to take off the training wheels now, if you don't mind. Integral of log x dx. So, for lack of imagination, I'll make the log x be my u, and I'll make the dx be my dv. Oh, I guess I'll leave the training wheels on, sorry. If you're excited about me taking them off, I feel like I've let you down. Sorry about that. I'll make up for it, don't worry. dv, dx. Okay, so du, what's the derivative of natural log? You got yourself a dx over x. What's the integral of v? Derivative dv equals dx. So v equals x. Yeah. So what you got here? You got yourself x log x minus the integral of v, which is x du, which is dx over x. And that gets us x log x minus the integral of dx, also known as x log x minus x plus a constant. And so, there we go. Another integral falls prey to the method of integration by parts. You know, it's a killing machine. Oh, I'm sorry, it's too violent. Let me try something else here. Let's see here. Any questions? All right, so there's one like sort of obvious question. How am I choosing u and v, right? How do I know which part to make u, which part to make v? Yeah? Right. Yeah, I think that's a good rule of thumb. There's also this, and I'm sharing this with, I didn't make this up. It was told me by a Calculus 2 class, and I share it with Calculus 2 classes because it seems to be effective. And it doesn't make sense to me, but students like it, so I share it now. There's this rule of Liate. Liate tells you how to choose the u. Now, these are supposedly mutually distinct categories. I reject the mutual distinction of these categories, which is part of the reason I don't understand it. You got log, you got inverse, you got algebraic, you got trigonometric, you got exponential. So what you're looking for is you look at the integrand and you choose u on basis of first choice top to bottom. All right, so for example, the gold card of u choices, this example, logarithm. Oh man, that's the best. U is log. No doubt about it. Like you see a log, u is log, according to Liate. Is Liate a law of calculus? No. Can Liate be violated? Oh yes. Does it even make sense? Not entirely. Why am I telling you it? It amuses me, and it's usually helpful. This one, we put u equal to x. Why did we do that? Why not make u equal to e to the x? After all, I can integrate x, right? You see what you're saying is very good, but also useless here, because I can integrate both x and e to the x. Wait a minute. I'm pointing at the wrong person. Sorry. I was like, to put on my glasses. Okay, so where was I? So you look here, right? Log, inverse. Oh, algebraic. That's an algebraic function, so that's why we chose x, according to Liate. This example, inverse sine is an inverse function, so that's why we chose that one, right? Because it was there. And also because there was nothing else to choose. I don't know, it's sort of helpful. The reason it doesn't make sense to me, though, is because in my book, log functions are inverse functions. So, and exponential functions are also the inverse functions of logs. So, like, I don't know, it doesn't. But you guys don't think that way, so it's good for you. Ilate? Oh, the inverse and the log were switched? Yeah, it's almost like the log and the inverse are sort of mutually exclusive. Yeah, maybe it's more like a. I don't know.
What would you do if you had like inverse tan of like natural log of x?
Inverse tan, you want to integrate the inverse tangent of the natural log of x dx.
Yeah.
I mean, I'll try it. I'll try anything once. Let's see here. U, dv. Ooh, 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 ah, ooh. This doesn't feel good as I'm writing it. This feels bad. Because, yeah. I mean, we can still do integration by parts. This is the cool thing, right? like this is x inverse tangent of the log of x minus the integral of v to u, which is apparently dx over 1 plus log x squared. Because the x, so v is x, and the v and this x cancel, just leave me the dx over 1 plus log squared. This, what I'm doing, guys, is the derivative with respect to x of inverse tangent of u, right? Chain rule, 1 over 1 plus u squared du dx. But, I mean, I'm honored that you think that integration by parts is this powerful, but it is, in fact, not a universal tool. There are lots and lots and lots of integrals that we just cannot find closed form answers to. Now, I'm not sure this is one of those, but I don't know. It's kind of neat, right? We replaced this awful integral with that awful integral. So it's a thing. It's something. But as you can see over here, it's most effective when we can replace the integral we have with something that is known, right? That's kind of the goal. Let me try another one. Goodness gracious. Oh, yeah. What if you had the integral of, let me do something a little bit more ugly if I've got time. Ooh, I better not make it ugly. We don't have time. I'll stick with the unugly version of it. Integral of x squared e to the minus x dx. So here, going with Liate, I'll make this dv, and I'll make the algebraic thing the u. And I'm going to call them 1 and 1, because I happen to know where we're going. So u1 equals x squared du1 2x dx. dv1 is e to the minus x dx. v1 is minus e to the minus x. This is one of those cases where I would encourage you to leave the training wheels on, because, I don't know, we have a proclivity to make sign errors here. At least I do. u1, v1, minus the integral of v1 du1. Let me move the equals over here. So what's that? That's x squared times minus e to the minus x minus the integral of what? Minus e to the minus x. du1 was what? 2x dx. Let's clean this up. This is minus x squared e to the minus x plus 2 times the integral of x e to the minus x dx. Right? So at this point, I'm going to focus in on this integral right here, and I'm going to say, aha, this is my dv2, which is the same as dv1 for its worth, and this is my u2. So I'd integrate by parts again. So like du2 is dx, and v2 is again minus e to the minus x. And so I have x squared e to the minus x plus 2 big parentheses are your friends. Remember, parentheses are your friends. Let's see here. So we got ourselves a u2 v2 minus the integral of v2 du2. Putting in the details. Let's see here. I've got x times minus e to the minus x minus the integral of minus e to the minus x du2 was dx. Oy. And then finally, minus x squared e to the minus x plus 2, I'll distribute stuff here, minus 2x e to the minus x. And I've got 2 minuses. I get another minus from the integration. All right, so I get 3 total minuses. So I get a minus 2 e to the minus x plus a constant if I have not made a mistake. Hopefully not. It's a little bit trickier than our examples so far, but same bag of tricks, right? Now, to check yourself, what do? Yeah. Yeah, take the derivative and see if we get back to the original integrand. Also, of course, you can plug this into Wolfram alpha and see if you got the same thing. Right? I mean, it exists, and it's helpful. Right? I don't know. Think of it this way. You're training for a marathon, right? And you keep jogging up a mountain. Should you also jog down? No, maybe you should ride a car. Right? Doesn't make jogging up the mountain any less legitimate. So checking your answers with Wolfram alphas, I mean, it's fine, as long as it's not all you do. If it's all you do, well, like just using Wolfram alpha to do all your homework would be sort of like driving your car around town to prepare for a marathon. You know, I mean, it would be dumb. I guess it might work if you were competing against, like people who are also doing that. But some of your classmates are studying, so you're stuck. Sorry. I graded the quizzes. Well, I know that the quizzes don't mean anything just yet. Ask me again after the quiz Monday next week, then I'll tell you who's working in here and who's not. But thanks, guys. See you tomorrow. It seems hot in here.